Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to yet another week of our NPTEL on Nonlinear and Adaptive Control. I'm Shrikant Sukumar, Systems and Control IIT Kanpur. So we are embarking into the final week of our course on Nonlinear and Adaptive Control. I do really hope that you have learned quite a bit during this course on how to design and analyze robust adaptive control algorithms that can drive systems such as the drone, the aircraft, the spacecraft, the neural network that you see here in the background. As I have mentioned before, I'm always very open to hearing more about the sort of applications that you folks are working on or plan to work on using the tools and techniques that you've learned here. And I'm hoping to hear more about that from all of you. So what we were doing until last time was to look at a particular kind of adaptive control design which does not rely on persistent excitation anymore and only relies on having excitation for a finite amount of time. And this condition was, of course, called the initial excitation condition. And we, of course, saw how to do control design. We saw how it was a weaker requirement as opposed to your persistence excitation based design. And we saw both the advantages and limitations of this method. We also saw that it's possible to alleviate some of the limitations by slightly modifying the initial excitation design to add a certainty equivalence adaptive control term, right? So keeping that in mind, we uh, do hope that this sort of design method helps us to give some improvements, not just in theory. Of course, we've seen in theory that there are significant improvements, especially in the sense that you have these negative terms in your adaptive update law, which was of course not there earlier, right? So we do of course hope that this sort of improvement is also something that you see in the performance of the adaptive control, right? So specifically the numerical performance of this adaptive control. All right. So again, please try it out on actual systems, and please do report back. How it looks. How the performance looks compared with your traditional certainty equivalence controller. Yeah, and we would like to hear more from you. Now, where we want to go starting today is on discussing, sort of modern ideas, yeah, in adaptive controls. And this, the aim is here to make some connections with learning theory, which has become very popular. And of course, adaptive control is also uh, consisting of learning itself. So this is another, case in point that we will try to make, that parameter learning is essentially, an ingredient or a key ingredient of what you do in, deep learning, right? Albeit the algorithms that are used may differ, and but eventually the basic theory remains the same. So the key connection that we will try to make is with neural networks, and so deep learning, so multi-layer neural networks, which is essentially what deep learning involves. But before we do any of that, I want to point you and also talk a little bit about this particular paper. As we can see, this is a very, very recent article that that's come up in archive um, online, and of course I'll put this up in the course material also. This is by Anuradha Andaswamy and Alexander Fradkov. These are, rather senior researchers in the field of adaptive control and learning. So what I want to do is to sort of go over this paper, sort of give an overview of this paper in this session, and sort of get a feel for how adaptive control has evolved, what pieces of adaptive control we have sort of covered in this course, and of course, uh, what is left and what we've left out, of course, due to, again, lack of time in any course such as this. And we also want to see what kind of connections with learning has been made in literature. So this is a what we call a survey paper. So I'm going to mark it here as lecture 12.1. So our last week of lectures. So like I said, this is a survey paper. So we are not really going to do a lot of mathematics or discuss a lot of mathematics like we've been doing, but we look at how things have evolved. All right. So um, so of course, these are some of the highlights, of course, of this article. Um, so there have been advances in the last 70 years in both uh, in adaptive control, in both deterministic and deterministic continuous time systems, right, and also stochastic discrete time systems. Okay, so these are the two sort of dynamical systems that have been looked at extensively in the domain of adaptive control, right? As you can see, we have covered, of course, only deterministic and continuous time systems, which is why I'm going to mark it in a different color here. Right? Um, but of course, there exists a lot of literature and work on stochastic discrete systems in adaptive control also. Um, so so this article, of course, is sort of trying to connect adaptive control to learning. So it sort of um, looks at the developments that have significant intersection with parameter learning, and of course, I mean, uh, as they usually do in survey articles, there's a lot of references that you can go through and as part of different sections. And if you want to delve into a particular topic in much more detail, and so you will of course get a very good idea of how you want to proceed to learn a particular topic if you're interested in that from here. Yeah. Um, so so anyway, so we start with this article starts with some kind of a chronology, right? On how adaptive control went. So in from 50s to 65, you had a lot of work on deterministic continuous time systems, right? And this is the sort of work that we also discussed, right? So there was a development of what is called the MIT rule, which formed the core of adaptive control, um, and this essentially was a way of updating unknown parameters by a very standard gradient type formula. And what is that gradient type formula? It is this equation one that you see here. Right? So um, now here, the E is of course the tracking error that we are so used to seeing, right? Um, between this process output Y and the desired output ym, and the gradient is of course the gradient operator, and this gradient is taken with respect to the uh, unknown parameter theta, right? So so basically the idea is sort of a way of um, you know sort of a steepest descent kind of an idea that you have typically in optimization type algorithms. So this is essentially what was called the MIT rule, and this formed the basis of a lot of adaptive control algorithms. Um, so um, so basically, a lot of motivation for adaptive control came from applications in aerospace for for autopilot design and flight control, and this still continues to be the case. A lot of more recent work in adaptive control has been applied to autopilots in fighter planes, and these have been tested, have been field tested successfully, in fact. Of course, getting FAA clearances and security clearances, etc., is a different matter altogether. But they have undergone significant field trials. Yeah. So, um, so anyway, so basically, you know, so this is sort of what this section of this article talks about. Right? So, uh, so rather interesting set of topics on which there was a requirement to do adaptation of parameters and adaptation of unknown quantities. Yeah. So um, so anyway, so this is a sort of motivation for what, why, or how adaptive control for continuous time systems did come about. uh, there's also a discussion on this problem of pattern recognition and classification, and this was seen as a parallel development, yeah, in adaptation, right? And interestingly, they and a lot of course, there were very different kinds of researchers who were working on these topics, like Widrow, who is very famous. But then there were also folks from adaptive control and nonlinear control, like Yakubovich, who also were working on it, Fradkov, Polyak, yeah, and more recent works, right? So, so basically, um, the idea is that there was a common element in to a diverse set of problems in pattern recognition and signal processing, which is the determination of of a set of parameters or weights that leads to desired classification. Right. So eventually, there was also the notion of trying to identify parameters or weights and using basically just input output data. Right. There was no clear models per se, or the models were incomplete to a large extent. But the idea was to sort of identify parameters that would help describe the model, right? And basically, Widrow's Adaline filters is one of the big foundations for neural networks, deep and otherwise. Yeah. So these Adaline filters became the foundations for what became neural networks. Yeah. So very old, very classical works, right? Um, uh, so anyway, so very interesting. Now, um, it it was of course realized soon that this MIT rule proposed by Whitaker can result in instability, and of course, then there was a requirement to study the stability of this adaptive controllers, right? I mean, it was not just enough to figure out a way to adapt for the parameters, but of course, to find a way to formulate a stability framework for analysis and synthesis of adaptive systems. And this is where, uh, you know, there was a discussion, or there was a lot of delving into dynamical system notions. Many authors, I would again point you more towards Narendra and Kudwa, um, who are one of the seminal researchers in this area. And of course, Lyapunov's method was suggested, right, in lieu of the gradient descent approach. And this is what we learned, right, in this course. Most of what we did in adaptive control in this course was via the use of the Lyapunov's method, right? And you can see the origin for this is going as far as the 70s, right? So not just Narendra, of course. Um, this in a deterministic discrete time setting, this was being parallelly addressed by Yakubovich in Russia, right? So 68 and 72. So lot of different works. I mean, there was work by Landau, yeah, Wittenmark, amongst others. I mean, you will find these names in very very good books in adaptive control. Narendra and Annaswamy, Astrom and Wittenmark, Ionu and Sun. So Shastri and Watson, Tao, Christic. So uh, Fradkov, Kumar Varaya. So who did the stochastic systems? So these basically addressed adaptive control architectures for a range of dynamical systems. All right, with of course full or partial measurements and so on and so forth. So this was essentially, I think you can trace it to about, I would say, I mean, there's of course much more recent 2003, but you can trace it from 1975 to 85, 90, and so on. Right? So almost 15 years of work, uh, actually laid the foundation for stable adaptive control. Right. So I would use the word, stable adaptive control came about. Yeah, until then it was more like uh, there was a update law for the parameters which was coming out of some kind of an optimization rule, but it did not really guarantee stability of the system, right? So um so anyway, so this is uh, so we are already aware of this kind of a structure for adjusting the parameter. This is what came out of most of the adaptive control laws, and in fact we've also looked at update laws which look pretty much like this equation two here. Then of course there was this phi is the suitably chosen regressor, and you have K's which some kind of a normalization component or a weight, if you may, which we call the adaptive control gain. And then of course there was the development of the notion of model reference adaptive control, again something we studied in the stochastic systems domain. uh, Based on the work by Astrom and co-workers, you we the outcome of that was the development of what's called self-tuning regulators. All right, and again this has also been worked on by many other authors like Landau, Kumar, Clark, etc. All right, so of course then there were connections. In all these cases there were requirement for learning, that is accurate parameter estimation. Just like in signal processing, the Adeline filters and neural networks, you had the requirement for learning parameters and weights. Here also we know we have parameters if we wanted to estimate, right? So we in fact saw that in our in several of our lectures, right? So this sort of connection was also made in stochastic approximation framework uh, by Sipkin in his work, right? So so the idea is that there was this parallel and similar evolution into branches of adaptive control in deterministic and stochastic systems. So of course they were distinct tools, but this development was happening sort of parallel. Yeah. Um, so of course this adaptive control terminology remained in vogue in deterministic systems, but then in the stochastic systems framework, it was termed as self-tuning regulators. We of course did not cover any stochastic system self-tuning regulators in this course, but I would sort of strongly encourage you to look at that. Then of course 90s to present, there were many lot of new novel flavors, yeah, in adaptive control of deterministic and stochastic systems. um, so one of the things that was evident, was that both the gradient algorithm and the stability-based algorithm in the Lyapunov approach had robustness issues to perturbations such as bounded disturbance and unknown dynamics. And this was figured out in 80s itself, right? And so therefore there were several approaches that were developed in order to nullify this issue. This was due to Narendra. We saw the sigma modification, which was due to Ianu and Kokotovich, which was due to Narendra, um, and the epsilon modification, which was due to Ianu and Kokotovich, right? Um, so basically, we wanted to ensure that these adaptive algorithms also provided robustness to withstand non-parametric uncertainties such as bounded external disturbances. Right. So um, so either, of course, there was this connection to persistent excitation of exogenous signals, right? Or of course, we modify the adaptive control in a suitable manner, which is what is the sigma epsilon modification, right? So if you have persistent excitation, none of this was ever a problem. There was always nice convergence properties and all that. We saw this Narendra and Annaswamy's results and so on. Um, and if you did not have persistent excitation, we had to modify the adaptive law by sigma and epsilon modification. So this is what we learned, and this is what was a sequence of development. So again, this there was again a parallel, in the learning framework and the learning domain on regularization in machine learning, right? And then again, similar results in discrete time as well. So um, so um, so anyway, so this sort of highlights the parallels that you have in the discrete continuous stochastic framework that's happening, right? Um, so of course, then there was a large requirement for addressing parametric uncertainties that appeared in different uh, sort of cases, different sort of situations. And a lot of special case nonlinear systems were started to be considered in the 90s, right? So this was, started with Christick's work and then Slotine and Lee. And so a lot of focus on non-linear systems, because of course most real systems are non-linear. So just focusing on linear systems or linearizing systems was not always a solution. And these were based on methods such as feedback numeration, backstepping, and averaging. So we did, of course, look at the backstepping based results, right? We did look at the backstepping based results mostly due to Christick, and of course some of them due to Slotine and Lee. But then there were many authors. There is Lavretsky, Vakimian, there is Slotine, there is Annaswamy, Narendra Parthasarathi. So basically, a lot of authors who did, contribute to this area, right? So by the end of 80s, there was this 80s and of course in 90s, there was a focus on uh, you know, what is called reinforcement learning or approximate dynamic programming. So, and this sort of trend was highlighted by this paper in 92 by Sutton et al., which is basically reinforcement learning in direct adaptive control. So, in usually the works on control based on reinforcement learning, typically a performance index is introduced, right? And then the neural network is used to approximate either the predicted optimal value of this functional or the optimal control policy. So basically, a neural network is a function approximator, and we will see something later on. And the idea is that in this performance index, which is like a cost, uh, which is usually an integral cost. The idea is that we in reinforcement learning is to use a function approximator to figure out the optimal value or the optimal policy that will give the optimal value, right? So these, there were a lot of different terminology for these, and these are called either an approximate DP, a dynamic programming, or neurodynamic programming, or adaptive dynamic programming. So all of these, are sort of terminologies that have been parallelly used. Yeah. The thing to remember is that it's very difficult to give good analytical results in this setup, because of obviously the complications arising due to dynamic programming. Yeah. So different sort of as we are aware, I mean, we have seen there are many different kinds of problem statements. And I mean, this is the typical, deterministic continuous time system where you want y to track some kind of a desired yc. I mean, or you may have some kind of a cost to be minimized. We usually do the first. I mean, we've looked at y tracking some yc, and then of course we have these unknown parameters theta right here. So this is the sort of framework we have, and we we've also looked at some kind of linearized versions of these, with some regressor parameter type structure. Okay. Um, of course, the goal is usually to send the error to zero, over time, right? And then this is what is the idea, right? Uh, Now, and the question is that if this can be ensured even when there are parametric uncertainties in theta, and also non-parametric uncertainties and several non-parametric uncertainties like modeling unmodeled dynamics, disturbances, etc. Right. So learning is always an important aspect of adaptive control, right? Because we are always trying to learn some parameter theta. Right? We of course look at this the certainty equivalence principle, which formed the basis of most of what we discussed in adaptive control, right? So that's the idea. I mean, basically, use the certainty equivalence principle is what came about of this, and a standard solution of an adaptive controller looks something like this. I mean, you have a controller which depends on some estimates of the parameters, some regressor, and time possibly, and then there is an update law, the parameter, which of course again depends on the possibly depends on the estimate itself and the regressor. Right? So this is sort of the structure of what you have. Then you of course have the linear version, it's the model reference adaptive control, where instead of following a reference signal, you follow a reference model. So that's this is also something that we have seen. One of the points that this article tries to make is that learning is essentially equal to parameter estimation. In adaptive control, very much so. In typical, setting of learning for control, also this is the case. More often than not, whether it be reinforcement learning or deep learning, you are trying to learn some parameters, right? So, and we did, many researchers established when such learning can happen, and these are connected to the persistence of excitation condition and uniform observability condition. We did look at this extensively, right? We looked at the work here, and in fact, mostly the Morgan Narendra paper in '77. So this is what we looked at. So this article is what we focused on mostly, the results that you saw, but we also saw further results. Um, then there have been some results on the notion of multiple models in adaptive control also. Um, um, but anyway, that's again another parallel sort of a framework is what I would say. Um, so so several interesting results on when parameter learning can happen, and we did look at this. I mean, again, so these were results from '70s and '80s, and we did look at some of these. Yeah. Um, Beyond that, there was a notion of robustness in adaptive control also, right? So um, the idea being that if there are unmodeled dynamics, time varying parameters and disturbances, how does the plant look? So in the frequency domain, we would have something like this, where of course d is some kind of a disturbance, and then n is some kind of a noise, and theta is some kind of a time varying quantity, right? Uh, so again, most of these results, these approaches on relied on properties of persistent excitation of exogenous commands. This is again Anderson, Narendra, etc. Or you modify the adaptive law. So these are again the results that connect to, this is basically sigma epsilon modification. Yeah, this is what helped impart robustness. Right? And so, of course, these are summarized in this result. Right. There is also this. I'm not going to discuss this in too much detail again here, but there has also been a lot of development on stochastic and discrete time systems, adaptive control in parallel. And as I mentioned, these have been termed as self-tuning regulators. Um, and a lot of this work has been due to Kumar and Varaya. A lot of different work connected to Varaya, Astrom, etc. So if you search these authors, you will usually find some results. And so there is also some little bit of a summary on what the self-tuning regulators, that is stochastic discrete time adaptive control results look like. So this is sort of what you have. And the idea is that the stochastic, the self-tuning regulator addresses the design of a minimum variance control, which looks something like this. And there is still the connection of parameter estimation and persistent excitation. I mean, that cannot, of course, be sort of given up, even in this case. I mean, the conditions for persistence may look different, but the requirement for persistent excitation still remains. Okay? So, um, and then finally, there is also adaptive optimal control for LQG type of situations, and this was also studied, where you have a discrete time system with unknown AB matrices, and you want to do some kind of an LQG control. That is, you want to minimize a cost which relies on uh, the the state X and also the control signal U, and you want to figure out how to minimize this cost whilst knowing that A and B are unknown and in the presence of noise. Yeah, so this is also uh, something that has been looked at. So has been looked at and formulated here, right? So um, so these are the sort of rather interesting sets of or the interesting progress of how adaptive control has moved forward. Now, what we want to do in a subsequent session is to also look a little bit more at how this progress has happened. So, I mean, forgive me if you may for introducing you to some history in adaptive control. But what I did want you all to see is how the thought process of this innovation went. Yeah, I mean, there was a need based on autopilot aircraft flight systems. Then came about some optimization based rules like the MIT rule for parameter updation. And then it was figured out that these were inadequate. So then stability mechanisms were developed. And then stable adaptive controllers came about. Then there was a realization that there is the stable adaptive controllers also do not guarantee robustness against disturbance and unmodeled dynamics. So then there was the notion of sigma epsilon modifications, persistent excitation for parameter learning, etc. And again, in parallel to all of this, there was the learning theory that was getting developed, Adeline filters, and where also parameter identification was essential, persistent excitation was formulated. Right? And then there was, of course, the self-tuning regulators in stochastic, discrete time systems, which we did not look at in our course. But that is also a very, very large set of literature that's out there in adaptive. So I hope you got a good feel for how this adaptive control literature has evolved. I'm going to look at a little bit more at this article before we start into more discussion on the learning aspects in adaptive control. All right. Thank you and see you again soon.